In this video, we're going to start rules of inferences and proofs in propositional logic. So first, let me explain what a proof is. A proof of alpha from a set of woofs gamma, so this is capital gamma, this just means a collection of one or more well-formed formulas. It's a sequence of inferences or rules using the woofs from gamma and any extra hypotheses that result in alpha. And those extra hypotheses are also subject to rules and constraints. And we're going to talk about some of them today. Now, if we have a proof of alpha from gamma, we write gamma proves alpha. So this symbol, you can think of it as the meaning proves. So what do I mean by this? We can take English sentences in an argument form and we can translate them to propositional logic. So we've done this at the very beginning of the series. So if I am hungry, I get something to eat. I am hungry, therefore I get something to eat. Now we can represent this logically. So 1, if I'm hungry, I get something to eat. So this is H arrow E. I am hungry, H. Therefore I get something to eat, so therefore E. So what we do is we set up our hypotheses and we use rules on certain lines and we justify them to get to our conclusion. So this is a simple application of something called Modus Ponens, MP, so we can use that in order to get E. In this video, we're going to learn 5 rules, do a couple proofs with those, and in each video we will introduce new rules and the proofs will get more complicated. We're not going to deal really with sentence translation. That's not what the point of these videos are. The point is to have something already in translated form and to get from A to B, because that's the most difficult part. So the first rule we're introducing is called reiteration. And I should really explain how these proofs work first. So whenever we start a proof, we have a line, and what we do is we put our hypotheses above that line, and all of our inferences occur after it. Now, you can add more hypotheses at any point, as long as a rule is being used, and we'll talk about those rules, by starting a new proof inside. So you can add in a new hypothesis that has to eventually conclude. So if you have, let's say, some hypothesis A or some line earlier in the proof, and you have a new subproof B, so you're introducing like an extra step. At any point, what we can do is we can reintroduce something from outside the proof. So let's say in line K later, we can take it from line I and we can reiterate it with R. Now in some systems, you just assume that everything's already there, but reiteration is a way of explicitly introducing it again. It's sort of like in our truth trees when we had branching paths and we introduced that variable in again, just to make it explicit. Okay, so we'll see reiteration in action a little bit later. Basically, that means that if you have something earlier in the proof, you can just copy it again. Conjunction introduction is nice. So if we have 2 lines I and J, where you have, say, A in line I and B in line J, then later, let's say in line K, we can introduce A and B. So what we do is we write which lines we get it from. We got it from I and J, and this is what's called and introduction, or conjunction introduction. So basically this says if you have P and Q in a proof, you can introduce P and Q. So to show this more explicitly with this example, suppose we have 2 hypotheses that we're starting out, line 1 and line 2. We have P, we have Q. Then in line 3, we can introduce P and Q. So this comes from line 1, line 2, and introduction. So this makes sense from a truth table. P is Q, P is true, Q is true, therefore P and Q is true. The third rule we have is called conjunction elimination. So basically, if A and B is true, we know that both A is true and B is true. So there's 2 different ways you can use the rule. Either, I'll do this in yellow to make sure that we're seeing the rule in action. So either you can put A down, and you would justify this by saying, oh, line I, this was and elimination, or conjunction elimination. Or we could take B, and this would also be from line I, and this is conjunction elimination. So specifically, if we want to see the example with P and Q, let's assume that we have P and Q somewhere in our proof. Let's just say it's the hypothesis, for instance. Then right away in line 2 and in line 3, say we could put P in line 2 and we could put Q in line 3. And both of these would say, oh, it comes from 1, it's and elimination. Okay, and then later we could put them back together if we want to. So that's conjunction elimination and conjunction introduction, probably the most intuitive rules out of literally everything. Now, the one we saw on the very first slide was called modus ponens. Some people call this conditional elimination. I like modus ponens. It's just how I learned it. And we abbreviate that as MP. So basically, if we have A and we have A arrow B, we can just follow the arrow. So on line K, we can write down B. So you can justify this by saying from line I and line J, we used modus ponens. So basically, we just follow the arrow and get the consequent. Antecedent, then consequent. We had the antecedent, therefore we get the consequent. So this looks just like it did on our first line. Let's say we have P arrow Q. Let's put that first. Why not? And then we get P. In our third line, we can get Q by saying from line 1 and line 2, we have modus ponens. It doesn't matter the order of the 1s and the 2s. As long as we see those two patterns, no matter what order they're in, we're good. Okay, that's modus ponens. The last one we have is something a little bit more complicated. It's like the reverse of modus ponens. Well, not the reverse necessarily, but if you think of modus ponens as conditional elimination, you can think of this conditional proof as conditional introduction. So basically, at any point, we can start a new subproof. And if we add a new hypothesis P, and we end up with a consequent Q, we've essentially said, okay, what if we have P? Well, then we can get Q. So then in a later line, in line K, you can write P arrow Q. And what you do for this one is you justify it by saying from line I to line J, we've proven P arrow Q through conditional proof. So this is a hypothetical. This is what gives you that conditional. So this all has to be kept within the subproof, though. You cannot just take things from in the main proof and put it in there. Like you have to do everything within the subproof, and we'll see examples of that. So we just did that example before, but let's just make a new hypothetical example here on the right side, and let's do it with reiteration too. Okay, so let's say in line 1 I start with C. This is my only assumption. So we'll call this the hypothesis. And what I want to do with this is I want to prove that if we have A and B, then we have C. That's what I want to prove. So what I can do is I can start a subproof. I can say, okay, well, hypothetically, what if we have A and B? And we can add this as a hypothesis. So what if we have that? Well, in line 3, what we can do is we can say, oh, well, we have C as a hypothesis already. So we can copy that into our subproof. So from line 1, we use reiteration. I can write it R, I can write it reit. Okay. Well, at this point, we don't actually need our line to be this long. So let's just shorten that line a little bit to where it is. And what we've done now is we've proven that if we have A and B, then we get C. So in line 4, we can say, okay, A and B is our antecedent, and if we have that, we have C. So from lines 2 to 3, we had a conditional proof. So that would be the end of our proof. We've shown that if we have A and B, then we have C. And this just follows naturally because we already assume that C is true at the very beginning. So actually, what we could do here, just to really show you how powerful this proof is, you can take it from the very beginning. So you can consider the assumption from C as being a conditional proof. So in line 5, once we get rid of this little bar, we could say, okay, from C, we get if A and B, then we get C, and this is just a large conditional proof from 1 to 4. So this is essentially the same thing. If we have C, then we have if A and B, then C. So I like that example because it shows the conditional proof twice, and actually it shows you what you're really doing in all your proofs. When you have hypotheses, again, these are just like what ifs. So almost every proof you do, theorem or non-theorem, in a way, it's just sort of a conditional proof. I shouldn't say that for every case. Tautologies are not conditional proofs, but if you have any sort of assumption and any sort of conclusion, you have a conditional proof. Okay, so let's do some examples. That's really the more important thing, is just to show a bunch of examples. So I want to show that A arrow B and B arrow C gives us A arrow C. So let's set up a couple rows here. Sort our assumptions, 1 and 2. Our assumption is that we have A arrow B, and our assumption is A arrow C. So this is our hypotheses. You never know how big these proofs are going to be, so just give yourself as much space as possible. Now, we need to prove A arrow C. So what we should do is we know we're going to need some sort of conditional proof, because we have to assume A and we have to eventually get to C. That's how we get it. That's how we get the arrow in our final result. So in line 3, I'm going to set that up. I'm going to start a subproof. I don't know how long that's going to be. Let's just say it starts here. If I need a longer line, I'll make the line longer, and I'll assume A as a hypothesis. Okay. In line 4, what can we do? Well, I see that we have... Well, I should go back and I should fix my mistake here, because we have actually that this is B arrow C, not A arrow C. So I see in line 1 that we have A arrow B. So I want to bring this back into the proof because I can do something with it. So this comes from 1, and this is a reiteration. Now in line 5, because I have A and I have A arrow B, I have B. This is just an application of modus ponens from 3 and 4, or conditional elimination, because I have A and I have A arrow B, therefore I have B. And now I have a B here. Okay, well in line 6, I can reiterate B arrow C, because I can do something with that then. So from 2, I'm reiterating it, and then in line 7, I can take B arrow C, and I can apply modus ponens once again to get C out. So this is from 5 and 6, and this is modus ponens. So at this point, I've started with A, and I've proven C within that subproof. Therefore, in line 8, what I can do is I can introduce A arrow C using the conditional proof rule from lines 3 to line 7. So I said, well, what if I have A? And I've shown that with the assumptions I have, I can get C. Therefore, from 3 to 7, if I have A, then I get C. That gives us A arrow C. So that was the proof of example 1. If A, then B. If B, then C. Therefore, we have if A, then C. Let's do another example. This one's a little bit more. So if we have A, then we have not B and not C. If we have D, then we have E and F. Therefore, if we have A and not D, we should get not B and E. I'm going to turn on the lines for this one because I have a feeling that this one might be a little bit long. So I have 2 assumptions here. I'll turn the lines off at the end so that way we can see it in all of its beautiful glory. So if we have A, then we have not B and not C. That's our first assumption. Our second assumption is that if we have not D, then we have E and F. And we want to show that if we have A and not D, we get not B arrow, or not B and E. So because I see an arrow here, I'm probably going to have to assume that we just have A and not D and then see what happens. So let's set that up. I don't know how long it's going to have to be, but we can put some lines in here. So for my assumption, I'm going to say, okay, what happens if I have A and not D? So this is another hypothesis. Okay, well here we can use conjunction elimination. So 4 and 5, we're going to get A, we're going to get not D. And this is just conjunction elimination on 3. Okay, well at this point, I have A, I have not D, and in 1 and 2, I see some modus ponens potential. So in 6 and 7, I'm going to reiterate these rules so that way we can use them in the subproof. So if we have A, then we have not B and C. This comes from 1, it's reiteration. And then we're going to have not D, arrow, E, and F. So this comes from line 2, and this is reiteration. Okay, at this point, we can use modus ponens. So in lines 8, we have A. From line 4, we have A. From line 6, we have A arrow, not B, and not C. So we can use modus ponens to get ourselves not B and not C. So justification 4, 6, MP. In line 9, we can do modus ponens again with not D and not D arrow E and F. That gives us E and F. So this comes from line 5 and line 7. That's modus ponens. So these two lines right here, we get E and F. Now we have to remind ourselves, what do we want to prove? If we have A and D, we're trying to get that we have not B and E. That is our goal. So I'm going to use conjunction elimination on 8 to get not B. So that's 8, and that's conjunction elimination. On line 9, I'm going to use conjunction elimination to get E. Comes from 9, that's another conjunction elimination. So now I have not B and I have E on their own. So I need to make this line a little bit longer, so I need one more line here. So on line 12, I'm going to take not B, I'm going to take E, and I'm going to join them together, because we know those are both true individually, so they'll be true together. So from line 10 and line 11, that is and introduction, so now I have not B and E. So this concludes our conditional proof now, because we're saying if we have A and not D, then we're going to get not B and E. So for our final line in 13, we can say, okay, if we have A and not D, then we're going to get not B and E. And what does this come from? Well, from line 3 all the way up to line 12, that was a conditional proof. And there, we're done. We have shown that A arrow not B and not C, and not D arrow E and F proves that if we have A and not D, then we get not B and E. Okay, so if we take out the lines, this is what our final proof looks like. We should get rid of these colorful lines if we can. That way we can see what it looks like. Okay, so that was example number 2, a little bit more complicated than example number 1, but another good illustration of the conditional proof, reiteration, modus ponens, conjunction elimination, and conjunction introduction. Like everything we introduced was used in this proof. Now one more example. Show that A arrow B and C gives us if we have A and B, then we have C. Okay, here's an interesting one. It's interesting because you might think to approach it a little bit differently than how you should. So let's just set this up. Our only assumption we're given is that if we have A, then we have B and C. So that's our hypothesis. Okay. Well, we need to show that if we have A and B, then we have C. So what we have to do in this subproof is we have to make an assumption that we have A and B. Now you might be thinking, hold on, we just have A here, why don't we just use A as an assumption? But no, you have to take everything on the antecedent as an assumption, otherwise the CP proof will not give us if A and B, then C. So that's a new hypothesis. In 3 and 4, what we're going to do is we're going to use conjunction elimination. Now, do we have to actually get B? We don't need B, so let's just use conjunction elimination to get A. So 2, conjunction elimination. Why bother writing down B if we don't need to use B for modus ponens or anything? So we have A. 4, we're going to reiterate our hypothesis. If we have A, then we have B and C. So that's a reiteration from 1. And line 5, we're going to use modus ponens on A, arrow B and C to give us B and C. So from 3 and 4, we did modus ponens. Now at this point, what do we need? We need C. That's what we need. Well, C is in line 5. So we can use conjunction elimination on line 5 to get a C. At this point, we can exit our subproof. So in line 7, we can say, okay, if we have A and B, then we're going to have C. So this comes from lines 2 to 6, and this was a conditional proof, and therefore, yes, our proof is complete. We have shown that if we have A and B, then we have C, based on the fact that if we have A, we have B and C. So you don't have to write out everything. If you're doing conjunction elimination, you only have to do it on what you need. In every other example, I did everything because we needed everything. Why not? But in this case, there's no point in writing B again. Same here. Like, we didn't need the B here, we didn't need the B here, so why bother writing it out? Just write out what you need. Now, what do you need? That takes practice, that takes experience. The more examples you do, the more practice you get. You'll get a little bit more comfortable with it. So what I want you to try on your own are 2 more proofs. There'll be a solution video in 24 hours. If you can do these in the comments, fantastic. If not, that's all right too. Try them on your own, and we'll go over the solutions in the next video. As always, if you have any questions, post them in the comments below, and I will answer you when I can.